The estimate is that this kind of very strong events should happen once every more or less 150 years. So it's time now.
Is space weather like I think of weather, like, or is it really kind of something completely different?
Yeah, space weather is basically, we do more or less the same things. We have to do forecasts, we have different conditions, we have nice space weather conditions, we have more disturbed space weather conditions. So yeah, they can be pretty much compared.
So when we talk about like space weather, what is it essentially?
Exactly. So space weather is the weather in space, and it's completely, totally driven by the sun. But it's not this static ball of gas, of ionized gas, I should say, which is known as plasma. So it's just not this static ball that is just there in space. It goes through a lot of activity. And actually, the activity of the sun is dictated by what we call the solar cycle. So every 11 years, we will have the sun alternating between a state of being a bit more quiet, which we call the solar minimum, and a state of being much more active, which we call solar maximum. And solar activity manifests through things such as eruptions, and parts of eruptions are, for example, solar flares or coronal mass ejections, CMEs, and other phenomena. So, for example, we have the solar wind streaming all the time from the sun continuously, and all of these things that happen on the sun can obviously affect other objects in the solar system, including Earth.
What is it though? Like, is it radiation? Is it just pure energy coming at us? Like, what is the thing that is happening, I guess?
Yes. So, and now it's going to be a pretty long conversation, but bear with me, and please feel free to stop me at any point. So, for example, when we have a solar eruption, we have some magnetic structure, magnetic bundle of magnetic fields that is there that somehow becomes unstable. So a solar flare is this very rapid burst of energy, of magnetic energy, that we see as a very fast brightening on the sun that can last from a few minutes to a couple of hours. And from there, yes, we get radiation coming out in the solar system. And at the same time, we can have also a so-called coronal mass ejection, or CME, coming out of the sun. And that's literally a cloud, a huge cloud of plasma and magnetic fields that can be thrown in any direction. So sometimes it's going to miss us, but sometimes it's going to directly impact us. Now, from a flare, we can get radiation, and also from a CME eruption when it's still very close to the sun, so it's still full of energy and can accelerate particles. We get these special particles that we call solar energetic particles, that are particles that are accelerated to such high energies that they are giving out a lot of radiation. So if and when they impact us, depending on how strong this level of radiation we have here, we can have something that is called a radiation storm. And that's what is actually dangerous for spacecraft in space, because this radiation can damage their electronics. And we have had occasions, or like some episodes, of losing some instruments on board some spacecraft, or losing a spacecraft altogether. And also these radiation storms, this radiation is very dangerous for astronauts, which also connects me to the next point. So Earth has its own magnetic field that generates this bubble of magnetic protection that we call the magnetosphere. Now, the magnetosphere is, if you look at it, now let's try to imagine, it's basically a bubble that is stretched enormously on one side, and the side on which it's stretched, it's the side that points away from the sun. And that's because we have the solar wind that I mentioned before coming all the time towards us and stretching these magnetic fields away from the sun. It's basically the same concept as if you are blowing your hair with an air dryer, and you will have the hair going all on one side, right?
I was imagining like somebody drawing a tennis ball, like when they draw like the wind going
Yes.
over it. And it's like that's how I would imagine it.
Yes, exactly, exactly. Something like that. So now, for example, but inside this bubble, we have a lot of protection from Earth's magnetic field itself, right? Now, when we have a coronal mass ejection coming towards us, which are these huge, huge clouds of plasma and magnetic field, they have their own magnetic field, obviously. And when the magnetic field coming from a CME is pointing instead southward and it's hitting Earth's magnetosphere, a process called magnetic reconnection happens where the lines merge and then separate, which means that Earth's magnetosphere will literally open on the day side. The magnetic field will be thrown back towards the night side, and we have extra particles and all this solar wind material from the sun that can flow straight into the poles, which is also what gives us auroras, which is at least in my opinion, it's the most beautiful spectacle that can come out of solar activity. And I think it's the only visual, literally visual, at wavelength that our eyes can see. It's the only visual manifestation of space weather. But what else can come when a coronal mass ejection with a southward pointing magnetic field comes towards us is that we get all these extra particles, extra currents coming in. So we will have elevated currents on ground, which can disrupt things like power lines and energy transformers, all these technology things that we are so accustomed to right now. But there is no direct effect on human health on the ground.
So it really kind of like the only thing it could really do to us is kind of like knock out our electronics, which would then cause global chaos.
Yes. And one other kind of storm that we can have is called a radio blackout, which means that on the day side, radio waves cannot transmit properly.
So there's basically, when we get down to it, right, like the solar wind, a solar flare, and a CME.
Yes, these are the main things that we have to be afraid of. And obviously solar flares and CMEs are what accelerate solar energetic particles.
So if we didn't have that magnetic field, are we just toast basically?
Probably yes. That's literally what's happening on the moon. So the moon has no magnetic field of itself, apart from probably something localized on the crust of the moon, but there is no large scale protection. So, which is okay, apart from the fact that we couldn't breathe because there is no atmosphere. But if we ignore the fact that we couldn't breathe, yeah, we can't have just someone on the moon staying there, because yes, when we have solar activity, there is enhancements of this radiation, but the solar wind itself is streaming particles continuously, which are not as energetic, but still, over time, radiation would still accumulate, I would say.
How's our magnetic field, right? Like there's no danger to our magnetic field or anything, is there? I hope.
No, our magnetic field is fine.
So if you were to kind of put like on a scale of 1 to 10, with 1 being like we don't know what this yellow looking ball in the sky is, to 10 we've got this whole thing figured out, where do you think that we would be kind of in our knowledge of what's going on with the sun?
On the sun, I would say 6 or 7. Maybe let's say 6.5. There is really a lot to still discover.
I guess what's going on with the sun? I don't know if that's a good question or not, but like, I have no idea what the sun really is. Like, I get it, but I have no clue what's really going on up there.
It's a middle-aged star, which means that it's at its phase of burning hydrogen into helium. We can think about the sun a bit like an onion. We have three major layers in the inside, which is called the solar interior, and then three layers of on the outside that we call the solar atmosphere. So in the inside, we have the nucleus, which is where all these fusion reactions happen. So where we're burning hydrogen into helium. Then we have the radiative zone, which is where the energy that is produced with these reactions is radiating outwards. Then we have the convection zone, which is where this energy is moves outwards through convective motions, where convective motion is basically like water boiling, where we have cold stuff going down and hot stuff going up. Or am I getting it the other way? Whatever. Anyway, we have these convective motions. And then we get to the atmosphere, where, as I said before, the lowest layer, which is the one we can see with our eyes, protected eyes, is the photosphere. Then we have the chromosphere, which is another layer that is kind of low in the sun. And then we have the corona, which is the outermost layer of the solar atmosphere, and it's kind of giant, like like we normal, like even if we look at places for example away 30 solar radii, so 30 times the radius of the sun, we still call that area the corona. So it's like a very the sun has a gigantic atmosphere. And then at some point we will have this transition from the corona to the solar wind, even if obviously the solar wind is formed much lower at the sun. And then at some point we will have probably after Mercury's orbit what we call interplanetary space. But then also after the planets, the sun is still influencing all the system. And actually the entire sphere of influence of the sun in terms of solar wind, or in terms of like what we study in heliophysics, which is the subject of studying the sun and its environment, all this bubble is called the heliosphere, literally the solar sphere, which is not as big as, for example, the sphere of influence of the sun's gravity. So for example, a lot of times, like when you talk about the solar system, like depends on what you're talking about, because the sun's gravity has an influence much farther away. So for example, where we know that the comets are born in the Oort cloud, that's way outside of the heliosphere. But the sphere of influence of the solar wind, so where the solar wind then meets the interstellar wind, that's what defines the heliosphere.
So that's out like way past Pluto, basically.
Oh yeah, by a lot. Yes.
That's the thing that always gets me whenever I hear about space, is like, this can't be real. All this stuff can't be real, right?
I know, it's so cool.
But I'm like, no.
But we have gone out of the heliosphere. We actually have measurements from outside of the heliosphere. We have had 2 spacecraft that have left it, or at least 2 spacecraft that have left it, and we have data of, which are the 2 Voyager spacecraft that were launched in 1977. I think that Voyager 2, so the second one, crossed this line of dividing the solar influence from interstellar space in 2018, so pretty recently. And yes, so now we have 2 probes that are actually measuring the interstellar winds.
So how far, like how many million miles is it out there before you finally get past it?
So I can do it more or less in terms of distance between the Earth and the Sun. So we are at 100 plus, so probably 120, definitely more than 100 times the distance between Earth and the Sun.
Whoa, that's pretty far out.
And the distance between the Earth and the Sun is 150 million kilometers, which in miles, I think should be something like 98 million miles.
So 98. So like, what's 98 times 100?
uh, 9,800.
9,800 million miles. Whatever that is.
So almost 10 billion miles.
That's insane.
That's a lot of mathematics for a Friday
I
afternoon.
know, right? Like, this is a Tuesday morning kind of conversation, not a Friday afternoon kind of conversation. But like, it's absolutely noticeable. Like, if you're on this side of the heliosphere, you know it, and once you're on that line, it's like crossing into the deep end or something.
I mean, yeah. I mean, it's not like a very sharp line. We have the same at the division between the magnetosphere and the solar wind. So actually, you know, as we can think of Earth's magnetosphere separating us from the solar wind, it's a bit the same in the case of the heliosphere being separated from the interstellar wind. But between all of these interfaces, there is something that we call a sheath region. So, for example, in the case of Earth, protecting us from the solar wind, we have the magnetosheath, and for the heliosphere separating from the interstellar wind, we have the heliosheath. So it's a region where materials from both sides are kind of mixing up, because the division is not extremely sharp.
So then are we ever affected by, you know, the solar winds or whatever from other stars?
No, the only thing that we get from outer space is galactic cosmic rays, which are very, very energetic particles that are coming from who knows where, the center of the galaxy, some supernovae, you know, so things that are happening outside in the galaxy. So we have these rays that come to us. And actually, funnily enough, we can see the solar cycle in the measurements of the cosmic rays, because when the sun is less active, so at solar minimum, we have a lot more cosmic rays coming, because the sun is not, you know, as energized. But during solar maximum, we measure a lot of less particles from the galaxy, because the sun is shooting stuff out all the time. So it's kind of protecting us.
It's kind of like a weak spot in a force field. That's the way that I imagine it, right? Like, it's getting through the force field at solar minimum and not at solar maximum.
Yes, exactly. Yes.
I understood. I understood that part, right? Like, I got that. The math was too hard, but I got that part. Are you ready for some harder / listener submitted questions?
Oh, we have listener. I didn't know. Yes, sure. Let's go for it.
Biggest solar weather event we've ever been hit with. What did it do?
Oh, I can talk for so long about this. Okay, I know the biggest, but it happened so long ago. So, okay, let's start. Yes, history. So if you have ever, like, if you're like a space weather enthusiast, or if you know a bit about the sun, you must have heard about the Carrington event, which was literally the biggest storm, geomagnetic storm, that we have had to date. Now, this storm happened in September 1859. So that was a long time ago, right? So it's known as the Carrington event because Richard Carrington, this amateur British astronomer, was looking at the sun when there was this big flare happening. So he actually did a drawing. Now, side note, there was another astronomer who did look at the same event, Richard Hodgson, but it's known as the Carrington event nowadays. Now, as I said, solar eruptions, we have flares and CMEs. They can happen separately, so we can have only a flare, we can have only a CME. In the strongest eruptions, they tend to happen together. So you have the brightening from the flare and the cloud coming off. The cloud, CME, coming off and hitting us is what drives then a geomagnetic storm, which is when I said we have the magnetosphere peeling and opening, we have all the particles coming in, we have auroras, we have extra currents going on ground. So that's all parts of a geomagnetic storm. So the cloud that was released at the eruption that Richard Carrington saw via the flare arrived to us pretty quickly, I think in about 1 day. We didn't have spacecraft, we didn't have satellites at that time. Astronauts were not even in the books, for at least another 100 years. But what did we have in 1859? The telegraph. So the telegraph system all around Europe and the Northern America completely failed. So there are even reports of telegraph operators disconnecting the machines, and the machines were still sending messages because of so much electric currents that were just roaming around on ground. Some operators got electric shocks, but apparently no. I mean, there are no reports of deaths, so that's great. But the point is that we have always asked, like, what? So one of the biggest questions in our field is what would happen if the Carrington event happened today? Because back in the day, the damage couldn't be that huge because we only had the telegraph going on as technological infrastructure. And as I said, there are absolutely, even from this kind of event where aurora was seen until the Caribbean. So there are reports from Mexico, from Cuba, and people said that they could just read the newspaper at night because of the aurora lights were so bright. But as I said, from something like that, there is absolutely no direct damage to the human body, only to the infrastructure. And damage to humans can only be indirect. But yeah, what would happen? We don't know yet. I mean, we obviously can do research and speculations, but something this strong has not happened since then on Earth. But we have had some other interesting events. So, for example, in 72, I think that the eruption was in August. It was a very strong eruption with related with flare and CME. The CME arrived to us very quickly again. What was interesting to me about that event is that, so the radiation storm, the one that comes very quickly because of these particles coming straight at us very quickly after an eruption, was so strong that, so this happened in August 1972, and we had one of the Apollos launching in April, and the next one launching in December of the same year. Had this eruption happened during one of the Apollo launches or missions, the astronauts, it has been estimated, they would have gotten enough radiation for actually getting cancer. So, and back in the day, we didn't know about the effects of space weather, because again, it's such a new field. Actually, the first CME observed was in 1970.
Can we predict them at all?
So that's what we are trying, and that's what space weather research, the field of space weather in research does. At the moment, we cannot really predict when an eruption is going to happen, at least not early enough. I mean, you can see some little precursors of an eruption right before it's happening, but officially, we cannot absolutely understand when an eruption will happen. After it has happened, we can try to forecast its effects on Earth. But obviously, again, we do not realize that, for example, for terrestrial weather, we've started working on predictions even before technology, but this field is pretty novel, so we have a lot to work on. But also because you have an eruption happening at the sun, and we don't have anything between the sun and Earth to keep monitoring, right? So it would be something like trying to understand the weather in Los Angeles by following one cloud that you saw in Central Europe.
Yeah, you can't figure it out, right? It's like, and I would imagine that even if we could put something up there, it still wouldn't be able to get us a signal faster than that thing's going to hit us.
I mean, for the particles, solar energetic particles, they're very quick. So when you're on operators, and I do work or at least meet up and conversate with people who actually work in the operations. I mean, that's like they have to be on call, because if there is like a medical doctor, and I'm like, but that's not why I did science. Like they have to be on call, and if there is some fast event, they have to immediately warn the astronauts and everything, and and launch alerts, and because these things have to be done extremely quickly, because these particles are quick. Instead, for CMEs, unless it's something extremely fast, I think that the fastest CME that has ever come to us arrived in 14 hours or 17, anyway, between 14 and about 15 hours, right, which is extremely quick. Normally they take about 3 days.
So when I think of like measurement, right, like I'm thinking of kind of along the lines of like the Richter scale, right? So if you took this event, is it Covington or Corrington? Carrington, mix of both of those, right? So where would that be on kind of like the measurement scale?
Okay, so that's a very nice question, because our scales do not like, there is a top, and above that it's still gonna be that. So I'm pretty sure it would. So for example, for geomagnetic storms, the official scale from NOAA is from G1 minor storm. I mean, obviously when there is no storm, it doesn't have a name. G1 minor storm to G5 extreme storm. So I'm 100% confident the Carrington event would have been classified as a G5. But we don't have anything above it. So the strong ones, they're still gonna be called G5, because the scale just doesn't go.
Right. It doesn't matter if it wipes the Earth out. It's still a G5.
And I mean, it's a bit the same for flares, more or less. So flares. Okay, let's only talk about the decent ones, because the scale goes very low and for things that we can barely see. But we have C flares, very weak, M flares, kind of medium, X flares, very strong. But they go on a logarithmic scale. So, an M flare is 10 times more powerful than the C flare, and the X flare 10 times more powerful. And then they have numbers inside. So you can have X1, X2, X3, X4. But for example, for M, you go from M1 through M9, and then you get to the X class. Well, the X class just doesn't end. So it has been estimated, obviously, from drawings done 150 years ago, that the Carrington event flare could have been something like X46, which is kind of crazy. but yeah, it would still be an X flare, because the scale just ends.
Man. But there's no indication that, like, okay, this happens every so often. This happens every, like an earthquake. Like, all right, well, every 300 years we're gonna get another one.
I mean, we don't. I mean, the estimate is that this kind of very strong events should happen once every more or less 150 years. So it's time now. No, I'm joking. But the point is that, okay, even if it happens, it could happen on the far side of the sun and just not come to us at all. So there has been in 2012 a pretty strong CME launched from the sun, but it missed us because it was just not launched in our direction. So these CMEs are very big, but if you consider the sun and all the planets being more or less on the same plane, close to the solar equator, so now we only consider 360 degrees. I mean, there have been CMEs that have been so large that they could almost cover 180 degrees, but on average they cover like 90 degrees more or less of the full circle. So there are many of them that just don't come to us because they are just going in another direction. So yes, the sun will pretty for sure have another huge eruption. When, we have no idea, and in which direction, we have no idea. So it could happen tomorrow and miss us.
Does it like move? Okay, this is maybe a ridiculous question or a brilliant question. Does it move the planet? Right? Like I'm just imagining this thing coming and bumping against our shield. Like, does it push us backwards or in any direction?
No. But it does compress the magnetosphere. So like the magnetosphere is very. I don't know. I like to think about it as something that is breathing with the sun, with the solar wind. So if we have like stronger, faster solar wind, it will compress on the day side, obviously. So the side that is facing the sun. If we have very slow wind and very calm conditions, it will bounce back out. If we have a very strong storm, it's going to be compressed, almost coming to very, very closer to like Earth's atmosphere and stuff like that. But the Earth itself will not change its path.
That's good. I'm imagining like somebody sitting on one of those exercise balls.
Oh yeah.
That's kind of what I imagine it's like. Like, oh, if you get a big one, it's going to compress it a lot, but it's still okay.
Yeah, yes, exactly.
I guess what would be your biggest fear about it?
I think that the thing that would worries me the most is probably astronauts' health, because these people are out there like exploring space and the cosmos for us, and I would like for them to stay in perfect health.
It kind of sounds to me like we should be very afraid and not afraid at all, right? Like it would ruin society, but we would live through it at least if we.
Oh, I mean, yeah. I mean, humanity survived for millions of years without even knowing about solar activity. We didn't have technology back then, but we survived. Yes.
Are governments or entities like doing something about this? Like, hey, one of these is going to hit us and it's going to be a big problem. We should probably prepare for this.
So some countries have started to declare space weather as a national catastrophe or national disaster class, as if as an earthquake, or just as something that to be aware of. Now obviously I'm more informed about Finland, which is where I studied at university, and obviously the US, because that's where I live and work now. So I will talk about the US. So in the US we have NOAA, the National Oceanic and Atmospheric Administration. I am the worst.
It's always something. It's NOAA. That's what I remember, right? Which order it is always like, wait a minute, what is it again?
Yeah, I think the National Oceanic and Atmospheric Administration. I'm the worst with acronyms, but I think it's correct. So they are the ones who do the official space weather forecasts and give out warnings. Not NASA. Aha. Did you know that? So they have this branch of NOAA called SWPC, Space Weather Prediction Center, where they do, and I mean, you can even go to the internet and look at their page. They have some nice overview pages where they show what the sun is looking out today, what the solar corona is looking like today, if there are any warnings out. What's the probability of a big eruption happening? So, for example, as I said, we don't know yet how to predict when an eruption will happen. But for example, what they do on NOAA is that they look at all the strong regions of stronger magnetic field on the sun, called active regions, and they look at how complex the magnetic field is, or how strong it is, and then they say, okay, if an eruption happens from there, what's the probability that we're going to have a strong radiation event? So things like this, it's all things that you can find on their website.
But is there anything that we can fundamentally do? We're like, no, technology operates on this, and and space weather would disrupt this, and it's like, there's nothing you can do.
No, I mean, the most important things to protect are satellites, because, even if I mean, obviously, I'm mostly interested in the scientific satellites, but a lot of stuff works on satellites. Some TV, I think, the GPS, of course, military satellites. All of these things are like there are so many satellites up there that contribute to our daily life, and we don't even know sometimes. So anyway, so what goes into preparedness to space weather is either shutting down satellites on time. So you know that something big is coming, shut down the satellite so that you protect the instruments. And for here again, for down on Earth, yeah, shutting down a transformer, going on backup battery powers, so all these things like to try to turn off the main systems until the conditions are back to being quiet.
That seems like a good plan.
Yeah, I mean, that's how we want to be prepared. Now, the hard part is to be able to exactly predict when something is happening.
How much time do we generally have, though, right?
For flares, or radiation coming from flares and the very initial launch of a CME, about 30 minutes on Earth.
Oh, that's not
a bit more on Mars.
That's not a lot of time.
Yeah, and then for the CME, which is the geomagnetic storm, but for the CME or geomagnetic storm, as I said, about 3 days. But if it's a very extreme event, 10-20 hours. If it's a Carrington level event, which is not something that we should expect.
Essentially, that kind of your research right now, like what are you working on? What are you finding? That kind of stuff.
In my daily life, well, first of all, I like to work on a lot of projects at the same time. So as probably most scientists, just to spice up your life a bit. But what I work on the most is what we call space weather research, as opposed to operations, right? Because operations are the people who have to look at the sun, predict what's going on now, right? Instead, I usually work on older events or like events that have already happened, and either use very complicated computer models to try to understand from a fundamental physics point of view what was going on with that event. And that would be to try to improve our knowledge of solar eruptions and the physics of these things coming towards us and driving storms. Sometimes instead, some other projects are about doing what we call hindcasts. So trying to use models that are a bit quicker, less complicated, and simulating what would happen if I had to forecast this event in real time. So trying to use only data that would be available in real time and see how the forecast would have been. Yes.
Is there anything that you think that we missed or anything like that? Or like, this is the coolest thing?
Maybe how we monitor the sun in terms of like measurements. Okay, so we look at the sun from Earth in a bunch of channels or wavelengths. Mostly we look at solar activity in so-called extreme ultraviolet, which is a bit stronger than ultraviolet, which I'm pretty sure that everybody has heard of, the UV. And where we can see a lot, like if you look at a picture of the sun in EUV, like it's completely different than what you would expect from just imagining the sun in the sky. There is so much activity going on, and all these loops of plasma and these very bright regions of stronger magnetic field, the active region. You see so much going on, and you can see these eruptions being launched beautifully. So that's what we look at to see, when an eruption will happen, or like the general structure of the solar magnetic field. Then we can look at the corona, which I said was the outer layer of the solar atmosphere that is gigantic, with a very special telescope that is called a coronagraph, which is a telescope that creates an artificial eclipse. So basically these telescopes and they're mostly based in space. but they have a thing that is called an occulter that is literally covering the bright solar disk, so that then we can reveal all the very, very, very faint corona. And there we can look at CMEs. So when they erupt, we see literally bright clouds moving away from the sun and becoming like by the time they are at about a few solar radii away from the sun, they're already tens of times bigger than the sun itself. Like they grow so fast, and they are very spectacular to look at. And then we have some imagers scattered that look at the space between the sun and Earth, but nothing that is fixed, looking always at the same space. But then something that is very important is that we have our solar wind monitors at the so-called point L1, which is the Sun-Earth Lagrange point L1, which is one of 5 very special points in space where the mutual gravity between the sun and Earth makes them stable. So if you park a spacecraft there, it's gonna be there with using very little fuel, and it's literally a parking spot in space. People who are interested in astronomy might have heard of L2, which is the point where actually the James Webb Space Telescope is now. So L1 is between the sun and Earth, just 1% ahead of Earth when you consider the full sun-Earth distance, and L2 is behind Earth. And the James Webb Space Telescope has to be there because it's using Earth as a screen from the very bright sun, because to look at the universe, you don't want all the light from the sun. So that perfect parking spot is perfect for James Webb Space Telescope. But we are interested in the sun, so we are on the other side, measuring at the spacecraft all the solar wind that is coming. So when we have a CME coming, we measure it at L1 about 30 to 60 minutes before it's going to actually impact Earth. So that's the warning time that we have at the moment, 30 to 60 minutes, where we are sure of what's coming because it has been measured. But obviously what we want is to have the lead time going to many hours, possibly days, right? So there are some mission concepts of like parking a ring of spacecraft at Venus's orbit. Venus is at 70% the distance between Earth and the sun. So which means that then the warning time would go from 30 to 60 minutes to about 1 day, 18 to 24 hours if we park a ring of spacecraft there. But yeah, we have a lot of mission concepts coming out. So let's see. I'm very curious to see what will be approved for flying, for improving our measurements around space.
That's kind of crazy, the idea that you can just there's a parking spot in space. Right?
Yes. And actually from ESA and NASA will contribute with one instrument. They are sending, I think that for now the plan is for 2027, 2029, but they will send a spacecraft at L5, at the L5 point that is 60 degrees. So if you're Earth and look at the sun, it's 60 degrees to your left. And from there, then you can see solar eruptions coming straight at Earth, much more easier than looking, from Earth at something that is coming towards you, which is, there are all these projection effects when you look at 2D images. So yeah, very exciting that we will have a mission that will be parked there at this L5 parking spot, and we'll look at solar eruptions for us.
And how much extra time would that give us?
It's not much about the time because we're not measuring, because that spacecraft will still be at the same distance as Earth from the sun. So but the point is that it's going to give us so much more confidence in understanding where eruptions are, like what their propagation direction is, how big they are, how fast they're going. So because when you have two well separated points to look at something in 2D images, then you can triangulate the thing you're trying to study and you get much less errors. So it is going to give a lot of improvements in terms of space weather predictions, but not in terms of measuring the stuff that is coming straight at us locally, but in terms of making predictions from afar.